Hello, this is a video specifically focused on effect sizes in relationships in multiple regression models. And we're going to start with looking at the combined effects of all the dependent variables that are present in what we call a model or a regression equation explaining variance in a single dependent variable by a collection of independent variables. And the question that we're trying to answer in here is, how well does this group of independent variables altogether estimate variance in y or the dependent variable? This is the test of this, the F test of this is like an omnibus test in ANOVA, but what we're interested in this particular case is the descriptive statistic, which is called multiple R at the correlational level, or more easily interpreted, multiple R squared. So multiple R, like any other correlation, is the measure of a strength of relationship. And the strength of relationship between the dependent variable y and the optimally weighted combination of independent variables, which is the prediction equation, including all of the x variables, x1, x2, x3, however many x variables you've given, and these are all based on the ordinary linear model. So multiple R is a correlation, and the kind of complex equation for multiple R is given there. We use the notation RY, that's your dependent variable, dot 1, 2. And this would really be dot 1, 2, 3, 4, dot, 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 K. I've just used an abbreviation for two independent variables in the model, but it would be RY dot however many independent variables you have. And that's going to equal the square root of the beta coefficient. This is a standardized term. It's on the level of a correlation of the first independent variable, that's 1, dot 2. So given that there's another independent variable. And with multiple independent variables, more than 2, it would be 1 dot 2, 3, 4, 5, dot, 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 K, representing all your independent variables. So it's the coefficient of the first variable given all the rest of the variables in the model times the correlation, the zero order, what we call the zero order correlation of R of the first variable with the dependent variable. We call that the zero order correlation. It's the simple bivariate correlation. And then another term would be the coefficient, the standardized coefficient for the second variable given 1, 3, 4, 5 until K. So, so the second variable's beta given all the other variables in the model times the zero order correlation of the second variable. And so on, you could have the beta of the third variable given 1 and 2 and all the other variables in the model times the zero order correlation of the dependent variable with the third independent, and so on. So another way of looking at this is that the multiple R is the correlation of y, dependent variable, with, it's a multiple correlation of y with all of the independents, which is going to be your correlation of y with your predicted y, given all the independents in the model. So for each independent variable you put into the model, if you remember that discrepancy between y and predicted y, you're reducing that to the extent that the other variables help explain variance, help improve your prediction. The points, as it were, are coming closer to the line, not really, but you can imagine that the amount that's unexplained is decreasing, and the amount that's unexplained is y hat, is the difference between y hat and y. So those are coming closer together. Your correlation R is getting larger because your discrepancy between y and y hat is getting smaller for all the predictive variables you're able to add. This is more interpretable if you square it, because if you square it, you can interpret it as a proportion of variance, in which case it's interpreted as the proportion of total variance in the dependent variable accounted for by the weighted combination of all the independent variables in the model. So it's the predicted y over total y. And standard deviation squared, it's the variance predicted y given all those variables in the model over total y variance. So that's your R squared. It is tested usually. It's it should be statistic. Its magnitude is usually descriptively more interesting. If you have a whole lot of variables, for each variable, you're going to add a little tiny bit of explained variance. And so you can inflate your R squared with a lot of variables in the model. And sometimes we have a very small R squared with a very large sample size that will be significant. So it's really more interesting as a descriptive statistic than its F-test. And that's one of the differences between ANOVA type studies and regression type studies, is that we are not particularly interested in a null hypothesis significance test, at least at the omnibus level. We're more interested in the tests of the individual regression coefficients. So we also have so this is a graphic of that term. I find that the graphics are very helpful. And what you'll see here, this is just a multiple regression model with two predictors, screen time and intelligence. And we will have looked at that in a class where in the bivariate model, we were predicting attention from screen time. And at a certain point, we're going to add a second predictor, which is intelligence. So we're going to be looking at the prediction of attention given both screen time, hours spent in front of a panel, and intelligence. And our total R squared is going to be the proportion of total variance in the dependent variable accounted for by all the independent variables in the model. So that's, if you look at the graphic, your total variance in Y is A plus B plus C plus E. I don't have a D there, but I don't. So it's all the regions of Y attention. Screen time predicts A and C. Intelligence also predicts A and C because they have overlapping predictive components, overlapping variants, as it were. But regardless of which of those two independent variables is accounting for the C component, altogether you have accounted for A, B, and C in Y. And so your total R squared, that's Y given 1 and 2, dot 1, 2, it could be more, is A, B, C, the three regions that overlap with the total variance over the total variance A, B, C, and E. We also, you will very often see a term called, you will always see in SPSS, a term called adjusted R squared. And adjusted R squared is not directly interpretable. So in reporting, we usually do both. We use total R squared, or what's called multiple R squared. And I think your textbook sometimes refers to it as the coefficient of determination. That is kind of an old-fashioned term, and you don't see it very often. But you'll report both total R squared, multiple R squared, and adjusted R squared, which is, you would never really calculate this. It's given in SPSS output. And that's because R squared is not an unbiased estimator of the population parameter. It's an inflated estimator. So, and that has to do with the fact that as you add independent variables, your R squared is always going to increase, even if many of your multiple predictors are only accounting for teeny tiny bits of R squared, just based on the matrices that are generated that are kind of fueling these relationships. Your R squared is going to be inflated. So to correct for this inflation, you report adjusted R squared. They adjust for the numbers of independent variables. So you'll see that as you add independent variables, your R squared will go up, your adjusted R squared will not go up as much. Sometimes it'll even go down. But you can't directly interpret it as a proportion of variance, so you report it, but I generally would not try to interpret it. I don't know of an interpretation that can be made directly, except you could say adjusted R squared, adjusted for the number of variables in the model. Now, one of the things that we have that we're very interested in, but is just a little bit complicated to interpret, it's not complicated, it's just a new term, is the partial correlation coefficient. And the partial correlation, and there's another also term coefficient like this. There are two of them, but we'll start with the partial correlation coefficient. And it tells you about the unique relationship of each independent variable with the dependent variable. And that's really very often what you want to know. What you want to know is how much an individual variable that you're using as a predictor is contributing to the explanation of Y. And what the partial correlation coefficient does is, as a correlation, it's the unique bivariate correlation of two variables. We're going to call it X1, which I believe was screen time, and the dependent variable. But you are what we call partialing out the correlation of any third, fourth, fifth, etc. variable in the model. And you're partialing that out of both the dependent variable and the independent variable. And there'll be a graphic of this in just a second, which is much more interpretable. But we use this if we're interested in explaining the unique variance in the dependent variable. Okay, so not total variance in the dependent variable, but that residual variance in the dependent variable after both the dependent variable and the independent variable are controlled for other predictors in the model, or after you're only looking at residuals that are uniquely explained by that independent variable. And I think that it will help a lot for interpretation to move on to our graphic. So we have the same graphic in the lower left-hand corner that you've seen before. If you remember, over there at the bottom right, you have the formula for total R squared, given the variance in Y, given in this case 1 and 2, the two independent variables in the model. And that is, as I said before, A plus B plus C, the explained parts, or the parts that are accounted for in all of Y variance by your independent variables divided by the total variance in Y, A plus B plus C plus E. So the way we write partial R squared is R1.2. And let me just warn you that the notation for partial correlation coefficient is not always the same. But I believe your textbook uses Y1.2. Okay, so that is the R squared between your dependent variable and your first independent variable given the second variable in the model. And we are, in this case, squaring the partial correlation for the purpose of interpretability, so that we can talk about variances instead of correlations. I find it much easier to think about these things in terms of variances, especially in explaining the graphics. So R squared, that unique component of the first independent variable in explaining the dependent variable given however many other predictors are in the model, is A. Okay, so that's the unique proportion of variance that is accounted for by screen time. Note that we do not include C, and that's because C is not uniquely explained by by screen time. It could, if you imagined you didn't even have screen time in the model, it still would have been explained by intelligence, that C proportion. So it's as if screen time gets no credit for the A prediction, or for the, C prediction. So the unique prediction of screen time is A, and that's why you see A in your numerator in the equation for R squared 1.2, or the squared partial correlation of screen time. So is A. I think that's pretty clear. And out of, as your denominator, not out of total variance in Y. Instead, out of only that proportion of variance in Y that is not otherwise explained. Only out of the residual variance in Y. And if you want to kind of parse all of that out in the equation at the far right, you'll see r squared y dot 1, 2 is your total r squared. You subtract the squared zero order correlation of your second independent variable with y, which is essentially b plus 2. And it's divided by 1, 100% of the variance in y, minus the squared correlation of y and the second variable, which again is b plus c. So you're only looking at the unique explanatory power of screen time on attention, given all the variance explained by intelligence, the unique residual variance in y. And the same for r squared y 2.1, the squared partial correlation coefficient for intelligence given screen time is a parallel equation. And remember, you could have this for as many predictors or independent variables as were in the model, in which case it would, for instance, be for the squared partial correlation of screen time with attention, it would be r squared y1 dot 2 through k. And it would be a over e, where e would be only that proportion of variance in attention that wasn't explained by anything else, any other independent variables, so a residual component of attention. So that has a slightly, there is a slightly different way of looking at unique relationships between independent variables and a dependent variable in multiple regression. That is called the semi-partial correlation coefficient, and it unfortunately also has another name called the part correlation coefficient. The SPSS reports it as a part. I am actually more familiar or more accustomed to referring to it as a part, but your textbook refers to it as the semi-partial. So that is a little bit confusing. But it is a different way of expressing a unique relationship. So we have remember, but then set aside the, let's call it squared semi-partial coefficient, which is the amount of variance accounted for uniquely by an independent variable divided by or out of the residual variance in the dependent variable after all other explained variants have been removed. Another term is the semi-partial correlation. And before we go to the squared semi-partial, just describing it in correlational terms, it's the correlation of one independent variable with the dependent variable, controlling that correlation for the effect of other variables. And it will be smaller than the previous partial r because your denominator is larger. And I'm going to go right to our graphic because that is going to be more explanatory. So here is our graphic of the squared semi-partial correlation coefficient, which is also known as incremental r squared, or also you'll see in SPSS, it's r squared change. So it's the incremental change in total variance explained as you've added a component. And it's the incremental proportion of total variance explained. And that's how it's different from the partial correlation coefficient, is that your denominator in this is all the variance in y. So you remember your total r squared, and I'm looking at the equations at the bottom, your total r squared for y given independent variables 1, 2, ... k is the variance explained by all the predictors, a plus b plus c, divided by the total variance in y, a plus b plus c plus e, which is what has yet been unexplained. So that's your total. A plus b plus c plus e is total y. What is explained by all two, in this case, variables in the model, is a plus b plus c. So it's the proportion out of the total. Your part, which I wrote down here, confusingly, I know, but it was what easily fit into the little box all the way at the bottom left, which is denotated in your textbook as r squared y parentheses 1.2, with the parentheses disambiguating it from no parentheses in the partial correlation coefficient, is still in the denominator total variance in y. But in the numerator, a minus b and c. So it's that proportion of total y variance uniquely explained by, in this case, screen time. Over to the right, there's the formula, total variance in the dependent variable, uniquely accounted for by intelligence. B minus a and c, anything that's accounted for by another variable, divided by total y. Now you may notice no credit is given to any predictor by c, and that is correct. No independent variable actually in either the semi-partial or the partial are given credit for proportions of variance that are overlapping between multiple predictors. So the interpretation of that is, there are multiple ways you can state it, but what you want to say, you want to be sure that the word uniquely is in your interpretation, and that a phrase indicating that that unique explanation is for total y variance given all the other predictors in the model. It's unique screen time given intelligence, given whatever else you have in there, over total variance. Whereas this is unique screen time over and above other predictors in the model on the residual variance in screen time after other predictors in the model. Or you could say the unique variance explained by X, controlling for other predictors in the model, both on on residual y. I suppose you could just say the unique contribution of screen time on residual variance in Y after other predictors are in the model. Okay, both of these terms remove from the, as it were, credit for individual independent variable explanatory power, the parts of its variance which is explained by any other independence. And I mentioned in here control variables, but basically just any other independent variables that are also in the model. Partial correlation coefficient is the correlation between the residual independent, that part that is unique to the model, with the adjusted values of the dependent, in other words, the residual variance in Y. Part or partial correlation contrasts the residual independent, that's part that is only unique to the model after any overlapping variance has been accounted for, with the unadjusted values of the dependent, in other words, all of Y variance. I have here, we will have gone over this in class, but without these terms over on the far right, we have the model, multiple regression model with two independent variables. The dependent variable is attention. And in this case, we are explaining attention through screen time and intelligence as measured by the RQ. And I believe that the class example, which was the simple bivariate regression, would have that screen time put in uniquely in the model as a single predictor, had a significant relationship to attention. IQ, if we have looked at that, or if we had looked at that, also has a significant relationship to attention. Note, though, that when they are both in the model, their relationships are no longer significant. And you may say, well, why is that? And that is because they have a very high C component. See, C, I've drawn it just in a convenient way here, but you can think A plus C, if you didn't have intelligence in there, is statistically significant in explaining total variance. B plus C is statistically significant, but uniquely on their own, neither A nor B is statistically significant. And one of the ways we can see that in output is that the zero order correlations, that's the correlation between screen time and attention, if nothing else is in the model, and you see that's quite large, and that's why in this case it's statistically significant, drops considerably when you look at either the partial or the part correlations, as does IQ. IQ has a moderately strong relationship at the zero order level, but it drops considerably when the other variable is in the model, as illustrated by the partial and the part. In other words, on their own, each has a strong correlation with the dependent variable, but when together they are concerned, neither has a substantial unique relationship with Y, whether you look at that as Y, whole Y, or Y with the part that the other variable Y reduced or adjusted for those parts that the other variable explain. So that's the partial and the part. And the The partial is larger than the part because the partial has adjusted the y, so it's only residual y, so that the residual y, which is in the denominator of the equation, is smaller. And if the denominator is smaller, the effect of the numerator will be larger. So partial is always larger than part to the extent that either variable has explanatory power. These are really important terms, and I wanted to put them in a video because I'm not sure when we'll be able to cover them in the class, but I want to be sure that you have this video as a resource, and we will definitely look at it in class, but it is a topic that you will probably want to go back to again, and I will certainly not have enough time, and I think kind of directly trying to get it in class is probably, it takes a little while to sink in. So that's our attention to our attention variable and the extent to which overall attention is explained by these two independent variables and their unique explanatory power.